All right, so we've been building to this point where we can start to talk about titration curves. So we've done acid-base pH titrations before, but now we can actually kind of analyze our graph and explain more carefully, more in detail, why we actually see what we see when we look at these curves, which is nice. The real kind of kicker, or the real reason we use these titration curves is because they're a really useful tool to be able to determine the equivalence point, to be able to work with calculations on unknown concentrations. It also allows us now to identify our unknown acids and bases based upon what we have got gleaned from our graphical data. We're going to be looking at one of these in the lab coming back next week. Originally, it was 2-day lab. We're going to cut it down to 1 day so we don't burn a whole week on one lab. But this is kind of where we're heading and what's coming up next. So just a reminder, when we start to look at these acid-base curves, here we've got just one you've seen before. We've got a strong acid being neutralized by a strong base. And a couple of things to note, a couple of things to notice. pH starts really low, reflecting that we have a high concentration of our acid particles, right? We're way down there on the pH scale, and we're adding base slowly over the course of our titration. As it continues to add, and we add a little bit of base, it immediately gets neutralized. Now there's less acid in the flask, and so our pH goes up a little bit and a little bit, until all of a sudden we get to this point where we're almost out of our acid, right? We've almost neutralized all of the acid. And now whenever we add just a little bit of base, our pH increases significantly. One drop causes us to have extra hydroxide, and we see the pH shoot up nearly 2 units on the pH scale. It is an incredible increase at that equivalence point. And so that inflection point, that steepest part of your slope, is always going to indicate to you that we have neutralized our acid or base. We've reached the equivalence point. For a strong acid, strong base, that then is going to be pH of 7. At that kind of midpoint, you've got exactly half, you've neutralized all of your acid, and so you've got water and salt. You're right at a pH of neutral 7. And you've seen this before. It's just nice to kind of revisit and talk about our graphs a little bit. When we start to work with weak species, things get a little trickier. So here we've got a weak acid. So you'll notice we're not quite as low on the pH scale. We're still titrating it with a strong base. We're adding a base, alkali, another term for basic alkaline. So we're adding a base, centimeters cubed, measures milliliters. So we're adding a base to this. And you'll notice there's a couple key feature differences. Here, there's this kind of plateau or flat line region here in the middle before we reach our equivalence point. And you'll also notice that our equivalence point is greater than 7 on the pH scale. These are the two kind of key giveaways that will tell us that this graph is a graphical titration of a weak species. So we're not at a pH of 7 anymore, and we've got kind of this flat line region in there. And so again, you'll notice that our pH starts a little higher. It's because we have less hydronium actually splitting off into solution. It's a weak acid, stays mostly intact. Our Ka is less than 1. Sorry, bring it back to equilibrium. It rises slowly, and it's this flat line region here where if you're thinking about what's in the beaker now, we started with all HA, we added a little bit of a base, and so now we have less HA, but it's still mostly HA. Now we also have some A- in there. We've got our buffer region. So this flat line region here is where you've actually created your buffer in your beaker just as a result of adding some base to your original weak acid. But equivalence point, still the steepest part of that slope. Now think about what's in the beaker at that point in time. If you're just, that's the wrong button. If you're thinking about what has occurred at that particular point in time, well, we've neutralized all of the original weak acid, right? We've used up all of the HA. We say that at this point, our HA concentration still equals our OH minus concentration. We've neutralized it completely with our strong base. But that means all of our HA has turned into A minus. And last year in college, we made an assumption and we kind of generalized this, but you now know better. The conjugate of a weak acid is a stronger base. If everything floating around is an A minus in the beaker, it could react with some water, right, to form some of that HA again, new HA, if you will, and some new OH minus. And that is why it is the creation of this extra hydroxide. That is why at the equivalence point, our pH is greater than 7. Last year, we kind of glazed over this. We kind of said, oh, it's because it's a strong base. It pulls it further. Well, that's not technically true. It's the fact that we've created now extra hydroxides as our conjugate base reacts back to its weak acid form. And so it's neat to kind of see this kind of full circle and think about it. But it is worth noting these major differences on the pH scales. pH curves, excuse me. If we were to flip it, sorry, so again, other kind of key giveaway here, if it's a weak acid, strong base, your equivalence point is going to be greater than 7. Kind of hit that hard, but get you the notes. If it was reversed, if we were doing a strong acid with a weak base, your pH starts way low. You do still have a buffer region here that occurs because you've now got a weak base and its conjugate. So you still have this flat line, but you'll now notice that our equivalence point ends up being below 7 on the pH scale. And this again is because of what particles are present in solution as you are running your titration. When you get to this point, you've neutralized all of the strong species and all of the weak base, but that makes a conjugate acid, and some of that conjugate acid reacts with the water, turning back into hydronium, and now we've got extra hydronium in solution, and so that's why our pH is less than 7. And so if you have a strong acid, weak base, your final equivalence point will have a pH less than 7 on the pH scale. So just things to look for when you're looking at these graphs to key you in on, okay, what types of substances did we react to give us the results that we're seeing? Yeah, cool. If we want to look at some actual examples here. So we're actually kind of highlighting the different regions. If it was a strong acid, strong base, our curve would start way lower and we'd have a much steeper region where our equivalence occurs. And we'd see kind of this gradual increase all the way along. For our weak acid, we end up with this buffer region kind of in the middle. And then there's this special point right here in the middle. And you'll notice that it is halfway between approximately the volume. And if we were actually, no, it is exactly half. Cool. I'm going to estimate here because this isn't quite 40 and this isn't quite 20. Our equivalence point is at 40 mils approximately, right? Half of that, we call it the half equivalence point. Here would be the 20 mils. And this is a special value. This is a special number for us to know, because if we're thinking about what has happened in the beaker, at this point right here in the middle of the buffer region, middle of the buffer region is where our buffer works best. You have neutralized half your acid. So now half of the acid remains. Well, what happened to the other half that you did neutralize? Well, it turned into conjugate base. And so at this point right here, we have the half equivalence point. And if you're thinking about Henderson-Hasselbalch, this point right here is the pKa. If we drop that over, that is the point where the pH will equal your pKa, which is a really nice graphical tool that at an instant, we can look at a graph and say, wait, okay, here's my equivalence point, half of that, carry that back over. Here's my pKa. And then if I do 10 to the power negative pKa, I'm at a Ka. And now I'm looking at a table saying, what is this unknown acid that I titrated based upon all of these Kas that we've already measured for known concentrations? So again, just think about the graph, think about where we're at, what's in the beaker, and kind of how we can start to follow through on that. Again, we see a pH that's greater than 7. For this one, it's 8.80. Phenolphthalein changes color between kind of our pH of 7 to our 8.59 on the pH scale. Here is where we could say we've got equal concentrations of these, that we've got half of this and half concentration then has changed into this. These concentrations are now equal. There's our pKa portion. Here's just, if we wanted to use a different indicator for where that buffer region is, we could use methyl red. If we were to look at some actual data here, so this is acetic acid titrated with sodium hydroxide. Again, our equivalence point is at 100. So at 50 is the half equivalence point. This would be where we can get our pKa. And so if we're looking the flip of that, if we were titrating a weak base with a strong acid, we see the same trend. We just kind of invert the graph here. We still have our equivalence point. Half of that gives us the pKa now of our NH4 plus, because this is still measuring pH. So it's going to be for our conjugate acid here. It gets a little trickier when you're dealing with bases because we got to technically flip everything, right? Because instead of measuring pOH, we're going to be measuring the pH. And so that's where it's a little trickier for navigating these, but it is still the same graphical analysis. You drop down, come back to half of that, and now you've got your half equivalence point. You could also, if you want to, then determine the unknown concentration using these two pieces. You could figure out what your concentration of your original weak acid or base was, but that's kind of reaching back to last year. Last one I want to look at real quick is if you got a polyprotic, if you got a diprotic or a triprotic, usually it's just going to be diprotic, but you end up with two kind of swoops. It's a double swooper. And so if you see more than one equivalence point, that should tell you that, oh, we had more than one hydrogen actually removed from our solution. And so here we've got this would be sulfurous acid. And so at the first kind of steep increase of our pH, that's the first hydrogen coming off, turning into the bisulfite ion. And then at that second swoop, we now have removed the second hydrogen, forming just the sulfite ion. And so as a result, because it's a weak acid and there's two H's, we end up with two buffer regions. These are going to be really unique when we look at their graphs, because you're going to see two kind of stark increases in the pH. Those are your two equivalence points. And then we've got our two flat lines or two buffer regions. But the math still works out the same. We just kind of have to truncate it into smaller pieces. If this is our first equivalence point, half of that is still going to be your first pKa, where half of your acid has been neutralized. These concentrations are now equal. And we can say that if we follow this back over, here's our first pKa or pKa1, if we're thinking about our diprotic acids. For the second one, it gets a little trickier because now you got to be thinking about, okay, here at this point, I've now neutralized all of the first hydrogen. So right at this point, it's now all the bisulfite ion. I'm going to now neutralize all of the bisulfite and turn it all into sulfite at the second piece. And it's the halfway point between those two data points that then gives us the pKa2, where we now have half of our bisulfite remaining, and we've made now equal concentrations of just the sulfite ion. And so a little bit different in the graphical analysis. It's still kind of cutting our graph into halves. It's just keeping track of what you've got. So if, again, diprotic acid, this is the first equivalence point, halfway between that is the pKa1. If this is our second equivalence point, it is the halfway point between these two data points that gives us our pKa2 if we follow that back. And so kind of arming ourselves with some tools that we can be using to start to use for our unknown acid titration. We'll be coming back next week to be looking at some of these titrations in the real world where you get the data and then you figure out that unknown acid. If you got questions, shoot them my way.